So last time we talked about space weather and the various storm scales that NOAA has implemented for this. The geomagnetic storms G1 to G5. We have the solar radiation storms S1 to S5, and the radio blackouts R1 to R5. So what I'm going to do is say a little bit about what is one of the biggest geomagnetic storms in modern times. And this was the Carrington Event. It was interesting because it was noted by Richard Carrington and Richard Hodgson. Carrington was an American astronomer and Hodgson was a British astronomer, that there were these major sunspot groups on the sun. In fact, Carrington had a line of sunspots that stretched across the sun almost like a big crack in the sun. Now, this is before the era of actually photographing these things, so he was sketching what he saw. And he sketched this particular sunspot group right here. And you can see on his sketch that we had several different umbras here, connected penumbras through here. But one of the things I want to particularly point out is in his sketch, there was this bright spot right there. Now, the bright spot, according to his records, there and also here and here, okay, these bright spots that appear in his record right there were not originally visible, and then as he was looking at the sun, these bright regions became present. Okay, this is what we know as a white light flare. This is most flares show up in ultraviolet light, and you see it in not so much in the corona, but you see it in the chromosphere, just above just below the corona, just above the photosphere. The white light flare, though, is actually visible on the photosphere in the region right around the sunspots. And so if you're ever looking at the sun and you see a bright white spot suddenly appear on the sun, that's likely a white light flare. Now, at that point, then it's like, oh my gosh, okay. Because what happened was just a couple of days later that magnetometers that were measuring the Earth's magnetic field, and they're already starting to realize there were small fluctuations in Earth's magnetic field. These magnetometers suddenly started having record activity since they'd started measuring it. So the magnetometers started moving around quite a lot, and they noticed that there were major auroral displays, and the aurora was visible as far south as Mexico, and telegraph outages. The telegraph lines, first of all, and this was all happening in just about 2 days after the white light flare. So that's when they started to realize there's a relationship between solar activity and geomagnetic activity. At first, what happened was that the telegraphs started running without having any batteries attached to them. Normally, to get telegraph, you have to actually connect to a power supply. They were running DC, so you had DC power supply, and so you had a battery connected, and so or transformer connecting here, and then but you needed to have some way of making it work, and so electrical DC, and so they noticed that all of a sudden that without having any power supplies connected, telegraphs were actually running just fine. In fact, running better than normal because you had so much electrical current running down them. We now know that the long stretches of wire were picking up fluctuations in magnetic field, and that was creating a huge voltage, and the huge voltage was making electrical current. Now, at first this was kind of cool, and then quickly became not so cool, because what happened was all the electrical current running down there was actually burning out the batteries and power supplies that normally would have been connected. Secondly, it became less cool of a thing because what happened was all the electrical current running down the telegraph lines were heating up the wires. And so they started to heat up. They kept in places that were catching fire and other places melting. And so you ended up losing telegraph lines. Now, this sort of thing, was a huge impact in the 1800s because that was the main way of communicating across long distances. I mean, the only other way of communicating across long distances in those days, other than telegraph, was you basically wrote a letter and gave it to somebody on a horse, and he galloped as fast as he could, until the horse got tired, and then they could maybe change out horses and keep going until you delivered it to your destination. That would take a lot longer. And so the telegraphs were the main communication. Now, if this were to happen today, you're not worried about telegraphs going down, but you're worried about phone lines, internet lines, and so forth going down. You're not worried about long stretches of wires running telegraphs. You're worried about long stretches of wires that carry electricity. Imagine all those high tension lines that run across the country going between power plants and cities, heating up and catching fire. And then you have to replace them. It would take decades to replace all those things. Not just that, but you also have the generators, the power plants, and then the substations, the electrical substations around the country blown out. You had to replace all those. And that'd be difficult to do because the factories that would be manufacturing all the parts would no longer be working because they'd have no electricity. And the trucks that would normally deliver all the parts would not be running because once they ran out of gas, the pumps, where they refill the trucks with fuel would no longer be working because they need electricity. And so all of a sudden you're talking about a major infrastructure failure that would be absolutely civilization ending for us. Because even people that have generators, they'd have electricity for a little while, but the generators eventually would need fuel, and then once they ran out of fuel, then they wouldn't be able to refuel them. Even natural gas powered systems would fail because the natural gas needs pumps that keep the gas under pressure, and those pumps would then fail if you ended up with loss of electricity. So the good news is that something like the Carrington event doesn't happen all the time. Otherwise, civilization, would be thrown back to the Dark Ages. But bad news is it does happen now and then. There was actually a coronal mass ejection in 2012 resulting from a major solar flare, and that actually was believed to be almost as big as the event from the Carrington event. Now, the good news is it actually happened on a part of the sun that was not directly facing Earth, and so it blew the coronal mass ejection off in a different direction, not towards Earth. So the coronal mass ejection did not hit Earth, did not create a major geomagnetic storm of the size of the Carrington event. And so that turned out to be very, very important. The direction matters for a coronal mass ejection. If it's headed towards Earth, then, and these are actually pictures here of coronal mass ejections from the SOHO satellite, and the one on the left shows a big blob of the sun's corona being blown off to the side, whereas the one on the right shows it coming in all directions. That's from one headed towards us. If it's heading towards us, then we know we're going to be having a geomagnetic storm, and that's when the Space Weather Prediction Center would actually issue a watch or a warning based on how bad they think it's going to be. And so this does matter what direction the coronal mass ejection is going to be.